This meeting is being recorded.
Good evening, Doctor. I am Sirin Chongling Singh with matrix number BI2510415. Today I will be presenting my solution of computer architecture assignment. For question 1A, we are finding the machine which consists of 256 KB of main memory and block size of 32 bytes and cache size of 64 KB. And for the question A, we will first find the address length, which is equals to the formula of log2 memory size, and we will get 18 bits. And for the word, we will use the formula of log2 block size, which we will get the 5 bits. And the line is equals to the log2 cache size over the block size, which we will get 11 bits. And the tag is using the formula address length minus the word bits and minus the line bits, which we will get 2 bits. And since each hex digit has 4 bits, and for this address we have 5 bits, so we will have 12 bits for the address length. But our machine is only needs 18 bits, so we need to cancel the first 2 digits in front. And then we will change the address into the binary and split into the 3 parts, which is tag and line and words, based on the bits that we found of the equation. Yeah. And for the question 2, and not the question 2, and for the address and for the address of 220E1, we will also using the same method, which we change the address into the binary, then we split into the 3 parts. And for the question B, we are finding which address will be mapped into the same line in the cache. So for this, we will also change the format into the binary and we split into the 3 parts. Then for this part, we are focusing on the line bits. So we'll compare the 3 address, the line bits of the 3 address, and we will get the answer of 21736 and 11736 can be stored into the same cache line since they have the same line field. And for the question C, we are finding for the fully associative. So for the fully associative cache, we only have tag and other offset. So of the offset is we are using the formula of log2 block size, which will get 5 bits, and the tag is equals to the address length minus the offset bits is equals to the 13 bits. And for the address of 11221, we will also using the method as before, so we will get this answer and split into the 2 parts. Also, we do the same with the address of 1FEFF. And so for the question D, for a two-way set associative cache, we are grouping the lines into the set, so we are finding the number of sets, which is equals to the number of cache line and divide by the number of ways. Since we do not have the number of cache lines, so we need to use the formula to find out the number of cache line first, which will get 2048 lines. And we put into the formula, then we will get 1024 for the number of sets. Then the offset is the 5 bits, which is same with the word bits, and the set is equals to the log2 number of sets is equals to the 10 bits, and the tag is equals to the address length minus the offset minus set is equals to the 3 bits. And also for the address of 1222 and the address of 34422, we use the method before and we split into the 3 parts. Okay, that's all for question 1. Then we will proceed to the question 2. For the question 2a, we are finding how many lines are there in the cache. So based on this question, we need to refer to the figure 1. In 1, there is 16 lines from 0 to F. And for the question B, identify the length of the memory address. So the address length, we are using a formula log to memory size, we will get 11 bits. And how many blocks in the memory? So we are finding the number of blocks using the formula of memory size divided by the block size. So it's equals to 512 blocks. And for the question D, if words are stored at the main memory address as follows, using a direct memory mapping as described in the lecture, which cache line will each map to? So first we will find the word line and tag, and using the formula, and then we change the address into the binary, then we split into the 3 parts. And also for this, we also focusing on the line bits. So the line bits is equals to the 001, which is equals to 1 in the decimal, and also equals to 1 in the hexadecimal. So for the address 344 will map to the cache line 1. And for the question 2, we also find out that the address of 3VB and the line bits of the address 3VB is equals to 1110, which is equals to 14 in decimal and equals to E in the hexadecimal. Hexadecimal. So the address of 3VB will map to the cache line E. For two-way set associative, we are grouping the lines into the set. So we are finding a number of sets, which equals to the 8 sets, and the offset bits is equals to 2, and also equals to the word bits that we found before. And also the tag, we use the formula, then we get 6 bits. And for the address, we will change it into binary using the table before that I drew out, and we split the part into 3: tag, set, and offset. So we're focusing on the set bits, then set is equals to 001 is equals to 1. So the address of 344 will map to the set 1. Answer for the address 3BB, we will use the method before, and we will get 110 for the set bits, which is equals to the 6 in the hexadecimal. So the address of 3BB is mapped to the cache set 6. And if a cache miss occur for data request, how does the set associative mapping handle the missed data? So in the event of a cache miss, the cache will load data from main memory into the appropriate set, which is the set 1. And since there is a two-way set associative cache, so there are 2 possible lines that can be stored in this data. So if both lines in set 1 are already occupied, which means full, and the LRU replacement policy will replace the line that has been used recently. The cache keeps track of the access history within each set to determine which line to replace. Okay, that's all for the question 2. And let's proceed to the question 3. And for the question 3A, how many bits are required for PC, AC, and IR? Since the machine is a 12-bit machine, so from the figure 2, we know that the opcode is equals to 4 bits and the address is equals to the 8 bits. And since the PC stores the memory address, so the PC is equals to the 8 bits, and the AC and IR stores and the AC and IR both stores the data in instruction, so AC and IR is equals to the 12 bits. For question 3B, we are tracing the execution of a 12-bit machine. Every instruction follows a 2-step cycle, which is execute, fetch, and execute. And for the step 1, the PC is at 00, so we fetch the 111 into the IR. And the step 2, the PC is increased to 01, and the value 002 from the memory address 11 is load into the AC. And for the step 3, 812, we fetch 812 into the IR. And step 4, we are doing a calculation of addition in the AC, which we add the values of AC with the values 003 from memory address 12, which we will get 005, and we store back into AC. And for the step 5, we fetch 313 into the IR, and step 6, the PC is increment to 03, and the value of AC is stored into the memory address 13. And in step 7, 112 is we fetch 112 into IR, and step 8, the value of 003 from memory address 12 is loaded into the AC. We fetch 410 into the IR in step 9. And for step 10, the PC is increment to 05, and we do the calculation of subtraction in the AC. The values 004 from the memory address 10 minus the values in AC, we will get 001 and store back into AC. We fetch in step 11, we fetch 311 into the IR. And for the last step, the PC is increment to 06, and the value in AC is stored into the memory address of 11. The execution stops. That's all from me.